what I'm going to show you now is we have these nifty little things these days in the 21st century that do all these calculations for you. When I was working in microwave, we had to do these things manually. And as I said, it's a very long and crazy logarithmic formula because it is a logarithmic formula. But now we have these handy-dandy conversion tools, which are great because this makes it much easier to show you this without driving you crazy with the math. So we're going to look at free space loss calculators. And basically what it does is it lets us put in distances in miles, kilometers, meters, centimeters, yards, feet, inches, whatever. We're going to use miles because this is America, and anybody can go to this Pasternak site and do it in kilometers for the European people, but it works the same way regardless. Next factor we have is the frequency that we're going to be using, and you can enter it in gigahertz or megahertz, and we're going to show you a little bit of demonstration of both, showing you that as the frequency goes higher, the path loss substantially increases. Then you have this transmitter gain and dB, and essentially what this is talking about is going back to this diagram. Coming off the antenna is your effective radiated power, and that's taking into consideration the power coming from the final amplifier of the transmitter going through whatever losses. There's cable loss, but we're not going to talk about that. And then finally getting to the antenna, which gives it another additional gain factor, which then gives you what is called an effective radiated power. So when we use this transmitter gain, it doesn't really matter what the power is initially, but the transmitter gain will give you an effective radiated power on the output, and that's all we're really worried about because we're dealing these equations in decibels. Now when you calculate free space loss and stuff like that, you don't do it in terms of watts, and I think this is done largely to just add another factor in to confuse people, and so they never think about it. The next thing we're going to do is, because we're not dealing in watts, which we're so used to using in our transmit power, we're going to be converting watts into decibels. You have two basic figures that are used in decibels. You have dBm, which means decibels with reference to 1 milliwatt, which is 1/1000th of a watt, and then you just have simple dB watts, which would be the watts. So basically, if we have 1 dB, there's basically a 30 decibel difference between dBm and dBw. So if we say 30, goes back to 0. 30 dBm is 0 dBw. And this is going to get really clear here in just a minute. So what I'm going to do, first of all, is we're going to take this free space loss calculator and we're going to find out how much power we have to be able to transmit over certain distances. And as you can tell here, I have already done a calculation of 250,000 miles, and I'm sure anybody that thinks about that, that would be equal to a one-way trip to the moon. So let's do what the amateurs are doing, the ham radio amateurs, and let's put in 146 megahertz. And let's say that the transmitter gain is going to be enter watts. Now, hams cannot put any more than 2,000 watts. They are limited to 2,000 watts. And they may be able to get a gain figure of 6 to 9 dB. So again, going back to our rule of thumb, if we have 2,000 watts maximum power input, which gives us maybe 1,500 watts at best output, and we give that through 9 dB, so we're tripling that power. So we go 1,500 watts to 3,000 watts is 3 dB, 3,000 watts to 6,000 watts is 6 dB, and 6,000 watts to 12,000 watts is 9 dB. So we have 12,000 watts ERP. So basically what this is saying is this is a 70 dB maximum power output, even with the best of circumstances. So let's go back to this. Transmitter gain, 70 dB. Receiver gain, let's give it that same 9 dB. Calculate it. Free space path loss is 108 decibels. So what does that mean? That means to overcome this 108 dB loss of power, now we have to go to dBW, and let's put in 108, convert it. That means that we have to have a transmit power, and you can see this is a big number, 448,734. So we're talking about 63 billion 95,734,448 watts.
Jeez.
Just to overcome the path loss. Do you see a problem here? And this is only going one way to the moon. Now let's look at something really ridiculous. Let's look at a distance, and let's all of a sudden now let's go to NASA's frequencies, and let's go to 10 gigahertz. And then we know the satellites can't put out a whole lot of power because they only have solar arrays on them. So let's say those solar arrays maybe are capable of delivering 10,000 watts, which is absurd. That's something that's actually classified. You know, we can just apply a little bit of common sense here to this. So transmitter gain, let's give them the benefit of the doubt and say that they can run 10 kW. So 70 dB, and now let's go to the sun. The sun is not an unreasonable example because what, Jupiter is a lot further away, right? 93 million miles. 10 gigahertz, there's our power. Let's give them the advantage of having a high gain receiver antenna, and let's give them 20 dB of gain there, all right? Calculate. Now we're talking about a free space path loss of 185.9 decibels. Well, let's go back to our decibel converter. So let's go 185 dB, which means that to make the trip to the sun, now we have to have petawatts. You're getting the idea here, guys. In other words, there is no freaking way on God's green earth that we can be making transmissions of these distances given the idea of how much power is on board these satellites. And of course there are other factors. There are other losses, there are other gains, whatever. But this is a very trimmed down version to simply show you, even if I'm off by a factor of 1,000,000 or even 1,000,000,000, it's impossible. It is impossible to make these journeys at these distances. This is the point that I've been talking about all these times. I have just used all mainstream sources, all mainstream information, everything, and I have shown, even in a physics lecture, how all of this works, the impossibility of transmitting a signal. You can't even be done to the moon, especially with what the hams can do. So what are the ham radio operators talking about when they say, well, we're doing these EME bounces? Well, first of all, EME bounce, if you're talking about a 250,000 mile trip, that means that you've got a 500,000 mile or 500,000 mile journey, that this limited power that the hams can use to go up there and bounce back. As I've just shown, this is patently impossible. So what is it that they're bouncing these signals off of? Well, I'm going to tell you, about 100 miles up, there's something that reflects RF radio waves. You can call it the ionosphere, whatever you want to call it. That is what it is that is reflecting these signals back. But as I have just shown, using all mainstream calculations and all mainstream science, the impossibility of it goes beyond silly. I mean, there's just no way that we can make these types of broadcasts. And common sense tells you that here on good old plain Earth, because if we have 50,000 watts and a relatively high gain antenna for AM radio station KOA, and we can barely cover the state, now we're starting to put things in perspective. And again, there are several other factors, but believe me, nothing that's going to make 1,000,000 or 1,000,000,000 times difference in these calculations. Do some research on these, do the calculations yourself, look up antenna gain factors, and also how far down in the mud or signals can be retrieved from ground noise level. A typical receiver sensitivity is minus 100 dBm. That's typical, some a little more, some a little less, depending on the frequency. Again, all these are factors, but the bottom line is that no matter what frequency they're using, and they would be far better off using low frequencies than they would be microwave, but even they won't make the distance, even though they have considerably less path loss. And anybody that has solar panels on their house knows that in order to power a medium-sized house, I don't know, 2,000, maybe 2,500 square feet, you need several panels on your roof. And then you're still only dealing with being able to power the house up to maybe 15 kilowatts or 15,000 watts, which is pretty typical, I think, for an average house, anywhere 50 to 20,000 watts, depending on how many electronic gizmos you have in your house and stuff like that. So this is kind of putting it in perspective. Think about solar arrays and people on the house. If people could generate megawatts, then you could sell power back to the power companies, and of course some people actually do that. But the typical solar arrangement that you see on people's houses, which consists of maybe 6, 7, 8, or 9 panels, are generating maybe 1,500 watts per panel, I would guess. My thing is to other electrical engineers out there, but I'm sure that somebody somewhere knows an RF communications engineer that can verify what I'm saying. And believe me, I'm using mainstream sources here, and it's pretty irrefutable. Anybody takes a look at this and thinks about it, you cannot debunk this. It is a simple law of physics that we operate from. Like I said, we had to do these path calculations manually back in the day when I did this. If you could just emanate a signal, an electromagnetic radiation ad infinitum forever with just any old power level, that would be great. But the fact is, you can't. And there is a very much defined threshold and limitation to these RF emanations. Again, these are known laws, debunk it.